All right, so we're recording now. So quick note, obviously did not, well, I guess not obviously. It was obvious to me that I didn't get your tests graded. But I'll have them done by next Tuesday. Probably could have gotten scores, but I want to make sure I don't miss anything and that everybody gets all their points and everything, so. But it's better to take a little bit longer. And get you all your points. All right, so where should we start with this one? Where's it good?
Remember when I started it, I ruminated with all of it.
Okay, because that's gonna give us a good target, right?
Yeah.
Go ahead.
Excuse me, rumination.
Yeah, so NBS.
Yes.
So that's gonna give us bromotoluene. Which now that gives us a pretty good target. We only need to add. We need to add 2 more carbons to our toluene, right?
Yep.
So acetylene.
Yeah.
And
NaH2,
good.
NH3.
So then we just put those together. Now we're actually most of the way there, right?
Yeah.
The hint tells us we're gonna use an acetate, it's gonna act as a nucleophile, that's gonna give us this piece, so we just need to put something there on that last carbon that's gonna be a good target for a nucleophile. But only one of them. So we probably want to start by doing a partial hydrogenation. Doesn't really matter which form, doesn't matter if it's cis or trans, right?
Oh, yeah, okay, yeah.
So if we did this with the.
I mean, it doesn't matter, so,
catalyst.
yeah. Doesn't matter, so.
So you use the dissolving metal one, that'd be fine for. Just for practical purposes, we wouldn't really ever use that if we didn't have to in the lab.
I don't remember using that for this, so.
Yeah, on paper, that's fine.
Yeah.
If we're actually gonna do it in lab though, we don't want to use dissolving metal if we can avoid it.
The first step I used HBr and roller. I don't know if that would be right. Not sure about that. That was
Anti-Markovnikov.
Anti-Markovnikov.
Only where it's SP2, so you have to.
So I'd have to double check that one to see if there's anything that says that you can't use that. It should be fine.
I just sort of
It's
used
still, actually, that one is an addition reaction.
Yeah, that's what I was saying, you
Yeah.
can only place it on a vanilla.
Yeah,
so that would make it go on to one of the other.
and it wouldn't even really react because we're gonna see in our next chapter after alcohols is talking about aromatics. But basically, we're not gonna break up an aromatic if we don't have to. That's one of the cardinal rules is you don't break up benzene rings. And doing addition across one of those bonds,
That's gonna be less stable.
that's gonna make it less stable all around.
Yeah.
We still have 2 conjugated bonds, but the fact that we broke up that ring structure makes it non-aromatic now, and that makes it super unstable.
First step.
Yeah, so you just, but you're still gonna get the rest of the steps as long as you, okay, so you missed this, but as long as you knew you were
I
trying to
got
get
it, yeah,
here.
I got there, got here,
Yeah.
and then
Lindlers,
all of this.
and then
Lindlers,
you probably want to brominate it, yeah.
and then we want to use the HBR drawer.
Gotcha.
Yeah.
Yeah, I remember.
Well, so that one's the anti-carbon.
Now that
On
matters,
the end.
exactly.
That's-
This is the one we guys, I don't understand, other one mechanism.
The free
Okay.
radicals.
Okay.
It is initiation,
Yeah.
propagation.
I wrote on the, it's not this, and I wrote the initiation steps. Just cause I was trying to, you know.
Yeah, show me what you do know. Yeah. Alright, and then once we get there, we're just gonna use the acetate. Acetate's not a great nucleophile, but bromine's a pretty good leaving group, so we'll get decent results. And this is a pretty. I like this one as a problem because it actually does show how you can make something that. Yeah, you can extract this from cinnamon trees, but you're not gonna get just this, you're gonna get a mixture of a whole bunch of other things.
Right.
With it as well. And cinnamon trees are really expensive and take a really long time to grow. It's a full
I
on
mean, if you're
tree,
just trying to get this compound out of a cinnamon tree, it's
Right.
what's even the point?
exactly. So toluene's really pretty common. Acetylene, we use it all the time, acetate's common as well, that's naturally occurring and really easy and cheap to produce. So, yeah, this is a 5-step process, but if it means we don't have to grow an entire orchard of cinnamon trees. That's probably
yeah.
cheaper. Which is also the difference between, artificial vanilla and vanilla extract. Vanilla flavoring is just vanillin in ethanol.
You can buy a whole humongous jug of
Right,
vanilla flavor for like
Exactly.
$5 compared to like a little tiny thing of vanilla extract that's $10.
vanilla extract is still mostly vanillin in ethanol, but it's got got some of those other impurities in it, and that's what gives it a little bit more well-rounded flavor. But also what makes it so expensive, you actually have to grow a plant and harvest it, move it around the globe.
The seeds are
The
extremely
seeds,
small.
they're small and they're fragile. Like the seed pods, vanilla seed pods don't travel very well.
Yeah.
And vanilla only grows in certain climates. Right, so you're also at the mercy of weather and climate change and globalism and how we, tariffs and all that are now causing issues, right? You don't have to do that if you just make it in the lab.
Right. As long as you purify it very well.
As long as you purify it very well. Couple of recrystallizations and you'll be fine. All right, let's look at. So our introduction to alcohols. We've been talking about alcohols for a while, but now we'll officially learn how to name them. So this will be on nomenclature section of the final. But it's the same thing we've been doing. We just add a new prefix and now we have OL at the end. Right, and like I said, we've been hinting at this and kind of dancing around it for a while now at this point. And all generally speaking, even larger compounds that have alcohol groups on them will mostly still end in OL. So THC, tetrahydrocannabinol, all, because it's an alcohol. For whatever reason, though, some compounds where the compound was known before the structure was known have some other names, like capsaicin is a phenol, but it's not really named as a phenol just because we've known vaguely what it was for a long, long time. And the key difference too is we'll actually talk about some different reactions of where alcohols react differently than phenols. This is another key when we're getting into the importance of aromatics and benzene rings, is that phenols in some cases will react differently than alcohols, even though it's just an alcohol on a benzene. that benzene gives it some different characteristics in some cases. And as we've said before, when we're naming these molecules, whatever the last thing is that you say is the one that's most important to keep the numbering low.
Yeah.
So the fact that ethanol, all is at the very end, means we want to keep that OH or that OH on the lowest carbon possible. That's more important than keeping like a chloro group or even an alkene. You want to keep the.
So the priority is higher with alcohols.
Correct.
Okay.
And in general, what we're gonna see is there is a list of priorities. If you look at the appendix of the textbook, there's a list of priorities for functional groups. But generally, as we keep going, whatever we've added most recently is higher priority. It just tends to go along that same route, which makes it easier. Whatever's most recent is most important. Alright, so here's the actual process pulled out from the Klein book. For naming alcohol, longest chain containing the OH group, number of the chain starting from the end closest to the OH group. Identify substituents, assign locants, which again that's our more specifically correct name for numbers. The reason we don't just say numbers is because there's a couple times, especially when we get into nitrogens, where we're gonna put things on a nitrogen and nitrogens don't get a number because they're nitrogens, not a carbon. And so in that case, we say it's an N-methyl group instead of a 1-methyl group. So the locant can be a letter in some
That's where I've
cases.
seen that from. I've seen a little bit of that. I was wondering.
Yeah, so in particular, you see it with amines. So cyclohexamine with a methyl group, we would say that's N-methyl cyclohexanamine. So it's not just the numbers that determine what, or that we use to specify where something is. Which is why this word locants even exists. Supposed to be alphabetical, but as usual, I'm not as picky about that as I am with the numbers and making sure that your name is unambiguous. And then do any stereochemistry. Right, so nothing new. The only difference is that OL. And just because this came across my feed the other day. So it's an older meme, but technically, you could make the argument that water is the simplest alcohol, but organic chemists don't like that. Technically, water is its own thing. But it's really just an OH group with a hydrogen attached to it, right? I thought that was funny. Let's talk a little bit about properties of alcohols. As we've seen before, in general, when we add more intermolecular forces, we're going to get higher boiling points and higher melting points. Melting points is not as strict of a relationship. A boiling point ties very, very closely to more intermolecular forces means higher boiling. With melting point, that gets a little hazy just because crystallization is weird and there's some things that can happen that keeping it in the crystalline phase can be different than keeping it in the liquid phase. But going from either liquid or a solid to gas, that's very, very easy conceptually. It's just breaking all the intermolecular bonds to do that. So more intermolecular forces, stronger intermolecular forces, higher boiling point. And if you have a bunch of things that have the same type of intermolecular forces, how do we know it's going to have a higher boiling point?
Surface area.
Surface area, why do you say that?
It's just like a larger,
Hydrogen bonds.
well, it's just more intramolecular forces that you have to deal with.
Yeah, so exactly. If they're all the same types of intermolecular forces. So each of these methanol, ethanol, and 2-propanol. All have one OH group. Every OH group you add is gonna increase your boiling point, because you're adding more hydrogen bonds by doing that. But if you're just adding more alkane groups to it, that's still gonna raise your boiling point. And it's tied to the surface area. Surface area plays a role when we're really getting into the fine details. But the first variable we look at is just which one's bigger.
Yeah.
More electrons means more van der Waals forces, more London dispersion forces, right? Going back to Gen Chem.
So.
Yeah, so more London dispersion forces. Is going to mean that your 2-propanol is gonna have a higher boiling point than the ethanol, which should be higher than the methanol. It does track pretty well. It's not as big a difference as this. Like, I wanna say that methanol boils at like 60 Celsius, so still a lot higher than chloroethane. But there is a noticeable difference there. And do I have that on the next slide? No. So here's a good question then. What about 2-propanol versus 3-propanol? They weigh the same number of OH groups. Which of those is gonna have a higher boiling point? Why?
Because it doesn't have as much steric hindrance, so therefore it has more surface area or space.
Exactly.
Taking up.
I was thinking just surface area, but yeah, I mean,
So it's a combination of both.
Steric
There's
hindrance.
less steric hindrance, so this can interact more strongly with the other OH groups. And this section, this hydrophilic region, can kind of like lay in more closely, more tightly. Packed and have more interactions with other groups. So when they're the
Yeah.
same size, whatever is the most linear.
Yeah.
It tends to be the higher boiling point. And so we'll use that term, the hydrophilic region and the hydrophobic region too. For alcohols, it's pretty much always just the OH group is really what we're talking about. It's gonna be more hydrophilic than anything else that we're gonna add on there. Anything short of a carboxylic acid alcohol is gonna be right up there. When it comes to solubility. Which would we expect to be more soluble in water?
that methanol over there.
Methanol. Yeah, in general, because in the way, this is a good time to actually talk about what's happening with solubility. Because we're not really adding more forces. If we have water, a bunch of water molecules floating around, they're all gonna mostly arrange themselves so that all the oxygens are pointed towards hydrogens and vice versa, right? Generally speaking, you get something that looks like that. In order for something to come in here and dissolve, we actually have to break apart. One of the ways you can think about this is we actually have to break apart all these favorable interactions to make a whole. And then we're gonna take our other molecule and put it in the hole. And if as long as it can make similar types of interactions, like replacing a water molecule with a methanol. That still fits relatively well. And we still get similar types of forces, right? But the bigger this group is that we attach, let's talk about
It's like the more room that it's.
the more room, the bigger hole we have to make, the more favorable water molecule interactions we have to break apart to make room for it. And so. Methanol and ethanol and isopropyl alcohol and propanols are all what we call miscible, meaning there's not really a limit to their solubility. You can dissolve as much methanol in water as you want to the point where it becomes water dissolved in methanol. And
Well,
that's
yeah,
that's the definition of miscible, means
Right.
that there's no limit to what your mole fraction could be. It could be 100% methanol all the way to 100% water or anything in between. It's not an emulsion. An emulsion specifically usually means that you have little droplets of something that's not soluble mixed in, and emulsions tend to be cloudy. So that's not a true solubility. Because what you actually get is little in most cases, most people have experience with emulsions when it comes to talking about like making a salad dressing or something like that. It's hollandaise, exactly. And so what you actually get is little hydrophobic lipid regions, fat bubbles floating around in vinegar or water. And those little droplets are what scatter the light and make it so it's not transparent, but give it that cloudiness. So that's same for milk. Milk is technically an emulsion. And so that's not a true solution. I guess it is a solution. It's not a homogeneous solution once you zoom in far. These, on the other hand, alcohols, we actually will dissolve fully up until you get to a point where your hydrophobic region is too big for the amount of favorable interactions you get. And we still get, we're going to come back to delta G again. Because when we're talking about these favorable interactions, which of these two terms are we talking about? Enthalpy or entropy?
Entropy.
Why? I'm open to it. Explain your reasoning.
I was just thinking because of like a greater amount of constituents on a molecule compared to, let's just say, whatever that one is compared to methanol.
Close, yeah, so the entropy does play a big role in this. The reason that these things match at all, like ethanol would mix with water, still shouldn't mix based just on the enthalpy. Because we're actually breaking apart extra hydrogen bonds to make room for something that doesn't have as strong of an interaction. But it does dissolve, and that's the entropy piece. Is because a mixture of two molecules is more random, it's more disordered than having two pure substances. So entropy pushes us towards mixing, but the enthalpy usually is going to be in favor of them staying separate because they already have, they're already maximizing favorable interactions usually, especially if we're talking about water. So there comes a point where your delta H term becomes bigger than your entropy term. And so typically we see that when we get to about five carbons per OH group. If you get more than 5 carbons per OH group, it's not going to dissolve in water. Because you have to make too large of a whole. You have to break up too many favorable interactions in that.
So that's what I was trying to
Yeah,
get at a little bit.
you were right there.
Close.
Right, so anything where you've got more than 5 carbons per OH is not going to dissolve well in water. And none of this is taking into account rate of solvation. Right, rate's its own thing.
Yes.
And that's why sugar, we know sugar dissolves in water, but it still doesn't dissolve instantly. Alcohol dissolves in water as fast as you can stir it, it's mixed. Sugar takes a little bit longer, even though it's got more favorable interactions. If you look at glucose, glucose is, let's see if I can get close to the structure here. I'm gonna get the stereochemistry all wrong. Point, I'm just trying to make. So up versus down is what separates glucose from, say, lactose. Is there one on that one? 1, 2, 3, 4, 5, 6, yeah. So you can see that it's a whole bunch of OH groups on glucose, on sugars in general, they all have that same general form. Most carbohydrates follow the general form of CXH2XOX. And every oxygen is an alcohol in this case, except for when they're in the ring form, it's a cycloether. So so sugars are like at a 1-to-1 ratio, alcohols to carbons, which is why they dissolve so well in water. But they do still take time. None of this is happening instantly. Unless
When
you're
you
mixing.
add heat, then it's gonna,
When you add heat, that speeds it up.
Yeah.
Plus, when you add heat. You got that T term, right? So the more random side gets favored when you raise the temperature. So solids and liquids get more soluble in anything. When you increase the temperature because you're making them more disordered. Gases get less soluble. As you increase
just
the
because
temperature.
they're already so disordered.
They're already so disordered that them getting dissolved into a liquid is actually less random than having them as a gas. So there's a couple things happening when you increase the temperature. One, you make things happen faster, but two, you actually favor more solubility for because you're increasing that entropy term. Other relevant properties of alcohols. They're antimicrobial, which we all learned a lot about during COVID and how to sterilize things. That wasn't something that was on everybody's tip of everybody's mind.
Everyone bought
Prior to
hand
2020.
sanitizer,
Exactly.
Hand sanitizer being $20.
Distilleries started making hand sanitizer instead of making vodka. In general, so there's a couple different things that can happen with these. If you have primary alcohols and phenols, they're pretty antimicrobial. And this is just some generic potency, like how antimicrobial are they? There's no units to it.
Just like a
This is
proportion.
just, yeah, by proportion. Basically, as you get longer, larger alcohols, there's sort of a sweet spot. Where they tend to be really antimicrobial. And then it kind of drops off, with the exception of if you keep going and looking more specifically. At something like hexyl resorcinol is a really common antimicrobial that gets used in a lot of things. And resorcinol in general, these alcohols are antimicrobial. This is a lot larger, so we would expect that to be in sort of that tailing off potency range. But there's actually a variety of different mechanisms by which these things have antimicrobial properties. The smaller alcohols, they interfere with bacteria and even viruses. There's a protein called peptidoglycan. And that kind of holds those cells and those viruses together. And peptidoglycan basically breaks that molecule, alcohols basically break that peptidoglycan molecule apart. And so basically you can't have a cell held together
This is
the
with
proteins.
bacteria.
This is with bacteria, but it
not
also,
archaea or?
It does also apply to viruses and archaea. Archaea don't have peptidoglycan,
Yeah,
huh? And because I'm not a microbiologist, I did find a good link to a NCBI article. The effect of disinfectants and antiseptics on co and cross selection of resistance to antibiotics. So this is more specifically or looking at a very specific. Oh, sorry, you're not looking at the same screen I am. I linked it next to the slides on the canvas. If you're interested in this, it talks a little bit about how different disinfectants work and how different sanitization methods work and their efficacy, right, with different pathogens. So, but I'm not qualified to really talk much about this. Carl could tell you much more about this than I could. But I linked you that article and I will read it as well when I have time. And we can talk about the various mechanisms. And there's some, so some viruses might have peptidoglycan but I think in general, certain ones do. And I think the other thing that these alcohols do is they do mess with the solubility, just like we were talking about. If you're dissolving something in water, as something that is evolved or adapted to live in living cells, so that includes viruses and bacteria, is going to be very, very specific to the solubility of all of its proteins and all of its different enzymes in water. If you put it in something that's not water, you can mess with how those proteins fold. And you basically disrupt what's called the tertiary structure.
A large part of protein folding is the hydrogen bonds.
A huge chunk of it is. And so just by doing something as simple as switching it from water to methanol, it's going to change how those proteins fold. And if those proteins can't stay folded the right way, then they're no longer active proteins. They can no longer actually catalyze reactions. As they misfold, as they unfold and refold incorrectly, they're going to stop being effective. And that's why one of the reasons why this is getting more into the microbiology than I'm really that comfortable with. But this is one of the reasons why vaccines work, is because if you just denature proteins, they're no longer dangerous. For the most part, there are exceptions to everything. But your immune system can still learn to recognize certain structural characteristics that are still there in the misfolded or the denatured state. And so basically you give your immune system a wanted poster, basically, with a hand-drawn portrait. It's not perfect, but it's enough that if they see something similar, they're going to key in on it. Without having actually needing the full infection to cause that. All right, and so that's why in the earliest, this is kind of gross. Nobody's eating, right? The earliest forms of vaccines were not actually true vaccines. Back in the 1700s, Benjamin Franklin's son died because he didn't give him the treatment at the time to prevent, I don't remember if it was measles. I think it was measles. Was basically to take the scabs from somebody who had measles and you dried them up and you ground them up and then you made a smoothie out of it. And sometimes that resulted in somebody getting actually really very sick from measles, but sometimes the drying aspect actually denatured the proteins to the point where they were no longer virulent, but then your body could develop resistance to it. And Ben Franklin's son died of the measles because he blamed himself for opting not to use this new technique at the time. Obviously, we've come a long way since then.
Right.
But even back in the 1700s, they understood that there was some element of prior exposure was really important. It was smallpox. Smallpox. All right. And as you see, other antimicrobials might still be alcohols, but they're gonna use different mechanisms. Hexylresorcinol, you're not actually gonna use that in large enough quantity that you're actually dissolving anything in it. So it's gonna be working by some other mechanism. And like a lot of antibiotics, they're gonna disrupt certain processes in these cells. And I don't actually know what the distinction between an antibiotic and an antimicrobial is. Come to think of it. Because they both are going to disrupt important processes in these bacteria, especially. All right, so let's talk about acidity. We've talked about acidity a lot, and just as a reminder, if you want to evaluate how acidic something can be, usually the best way to do that is you deprotonate it and then you look at how stable the conjugate base is. If deprotonating it makes something really unstable, it's not going to get deprotonated very easily. So like a carbanion is really unstable. And a nitrogen with a negative charge is slightly more stable. An oxygen with a negative charge is more stable than that. And our halides are the most stable deprotonated form. This is all ignoring resonance at this point. But basically, if we want to deprotonate an alcohol, we have to use a stronger base, a more unstable conjugate base. And just for to put some numbers to it, if you look at pKa's, pKa of an alkane is between 45 and 50. pKa of an amine is between 35 and 40. pKa of an alcohol is usually between 15 and 18. That includes water. Water's right around 15 usually. And then our strong acids, our halide acids, can be all the way from -10 to 3. Hydrofluoric acid is around 3. And I believe hydroiodic acid is -10. HBr and HCl are both negative, but I don't remember exactly where. All right, so if we wanted to deprotonate an alcohol, why would a deprotonated alcohol be useful for starters? Good nucleophile, good base, right? So for all of our synthesis steps. So we might think based on this, all we have to do to get to deprotonate an alcohol is put it with sodium amide. NaNH2. We use that to deprotonate alkynes. We don't actually see great yields when we do that. So if we wanted to take ethanol and deprotonate it to make sodium ethoxide, the two most common ways to do that are actually to use sodium hydride to make sodium ethoxide, or use sodium metal. Put sodium metal in ethanol, you get sodium ethoxide. Those both give us really good yields. Why would those give us such good yields? This is actual redox reaction, not just the deprotonate acid base. Is that going to affect the yield?
So the acid base, it's more like an equilibrium you're trying to deal with compared with this.
Yeah, what makes this irreversible and not equilibrium?
So
We've got a solid as our reactant here. Continue your thoughts. Go into an aqueous solution. And the gas. The gas is leaving the reaction system, right? So basically, we're making products, but one of our products is removed from the reaction as it's being made. So the fact that we're making a hydrogen gas makes it irreversible, because once the hydrogen gas is gone, it can't go the other way.
Because if you're doing an acid base reaction, you're still gonna have a certain amount of either the acid or the base that you have to deal with.
Exactly, and our best bases also tend to be good nucleophiles.
Right.
So if we just use sodium amide, now, we're gonna make some of the sodium ethoxide, but we're also going to make maybe some ethene. Maybe we'll go through an elimination reaction, or maybe we'll just go.
So there's a whole bunch of other stuff.
We got our SN1, SN2, E1, E2 step happening as well, and it's an equilibrium reaction. Now, it's an equilibrium reaction, it's gonna have a really high, think about those pKa's again.
Right.
The difference of pKa, 20 pKa units, that's equilibrium constant of 10 to the 20th. So it's less the equilibrium issue, and it's more the competing reactions issue. And if we just pick a different base, or put it through a redox reaction, we can eliminate both of those issues. Alright, and so now and we do have sodium, I think we have sodium methoxide in the stockroom. It's not terribly stable. It's better here than it is in more humid environments, because as soon as you get moisture mixed in with your sodium methoxide, you're gonna wind up with sodium hydroxide and ethanol. Because ethanol is a better base than water is, than hydroxide is. Sorry, I said that backwards. No, that's right. Ethanol is a better base than hydroxide is. So we're gonna wind up with it not lasting very long. So a lot of times we'll actually wind up, especially if you work in the lab where humidity is an issue, you generate your deprotonated alcohols kind of on the fly as part of your synthesis process, rather than relying on it being in the stockroom. Just because it'll have such a short shelf life. It's, like I said, it's okay up here because it's not humid. Even when it's humid up here, it's not that humid compared to most places in the US. All right, let's talk about phenols versus alcohols and their acidity, and then we'll take a break. See if we can come up with a couple reasons why might phenol be more acidic than cyclohexanol. They're the same size.
Theoretically be more stable.
It's gonna be harder to knock off that hydrogen
On which one?
on phenol.
Be easier to knock off hydrogen on the phone. More acidic.
Resonance structure, make it stabilize, etc.
So if we deprotonate a phenol, we get this. Phenolate is what it's called. Phenolate, yeah, has a negative charge, but it also has a whole bunch of resonance structures where we can resonate that negative charge around the whole ring structure, right? We can't do that with the cyclohexanol. We deprotonate the cyclohexanol, we get a negative charge on the oxygen, no resonance. So the obvious one, the obvious reason is the resonance. Right, and here's a figure of all the different resonance structures that you get. Remember, the more resonance structures, the more stabilization you get. And we wind up with a whole bunch here. And they're not all equally stable. This is still gonna be the major resonance contributor, because push comes to shove, they all have full valence. But a negative charge on an oxygen is just a little bit more stable than a negative charge on a carbon, just because of electronegativity. But they're all relatively close to the same strength. The other reason is something that's not entirely obvious yet. Benzene rings are what are called electron withdrawing groups. Because all of those resonance structures we just looked at, they've all put extra electron density into the benzene ring compared to leaving the electron density where it was. And so that's considered an electron withdrawing group, even though the oxygen is more electronegative than the carbon. All of those resonance structures means that the oxygen doesn't have as much electronegative, or doesn't have as much electron density around it as it normally would. Right, and there's a lot of different ways. The simplest way to look at induction is if you put more electron withdrawing or more electronegative elements around it. The trichloroethanol has pKa that's almost 4 pKa units more acidic than just regular ethanol. And that's just because these fluorines are literally pulling electron density away from the oxygen. If the oxygen has less electron density, it's easier to pull that hydrogen off. Right? I think you can think.
I think that's what I was thinking of with the phenol that I was just mixing it up.
Yeah, good. So the easiest way to think, a lot of times the easiest way to think about how acidic something can be is you can just treat that hydrogen like it's a magnet on a fridge. If you pull away more of the electron density, there's not as much magnetic force holding that hydrogen on. Hydrogen's got the positive charge, the oxygen's a negative charge, so we take away some of that negative charge, the hydrogen pops off easier. Right, and benzenes and aromatics in general do that because they have all those resonance structures that have all the electrons in the ring. Here we go. And again, let me fix my figure real quick. The other thing to consider is that the deprotonated state is the sterics of the deprotonated state. Once it's deprotonated, then the solvent molecules are all going to form even stronger interactions, right? Because what's a stronger intermolecular force than hydrogen bonds? Is an ion dipole attraction. And so once we deprotonate either an alcohol, the rest of the solvent molecules around it are going to kind of surround it with the partial positive charges to stabilize it. But that's limited by sterics. Right, you can't have as many solvent molecules around to stabilize it if you have a sterically hindered alcohol. So primary alcohols tend to be more acidic than tertiary alcohols, not by a ton. If you look at the pKa units, factor 10 to the 2, it's not nothing, but that's still in our normal range for alcohols.
It's sort of the same reason that the boiling point changes.
Yeah, more sterics around it, or more sterics around that means you can't form as many favorable interactions. And phenols are planar. Because they're attached to a big bulky group, but when you consider cyclohexanol versus phenol. Yeah, you've got one where you've got all these sp3. There, that's what I want to do. All these sp3 carbons are just physically taking up more space. Versus a phenol, yeah, this is a big bulky group, but it's flat and it's kind of pointed directly away from the oxygen. So you actually have more steric hindrance in the cyclohexanol than you do in the phenol. Right, and those three factors that I presented them as, this is why phenols are more acidic, but these are actually the three most important factors in determining any acidity. If we're trying to rank molecules based on acidity, look at it in this order too. The most important thing is, do I have resonance stabilization of the conjugate base? Or do we lose resonance by deprotonating something? There's a couple. Can that happen? Yeah, you can deprotonate things and lose resonance occasionally. And then you look at induction, and then you look at solvation in sterics. Most important down to least important. We were talking about a pKa difference of 10⁶ for the resonance stabilization, right? Versus 10⁴ with the induction, and then 10⁵ with solvation. So go in this order. Most important is the resonance. All right. Let's take a break, and then we'll do some practice with these, with the acidity, and we'll start introducing some reactions. So let's come back at 5 after.
They just canceled the class and I was really excited.
Oh,
There's a water quality monitoring.
oh, here.
There's, I figured that it was gonna be canceled because there was only me and some other person that signed up for it. And I kept on checking like every single day, but nobody's been signing up for it.
I wonder who they had to teach that.
It was,
Was it Dan Arcee? Scott's on sabbatical, right? Go ask him.
you know,
Dang, let's do that.
I've been having to deal with, so on my UC application,
Mm-hmm.
I accidentally entered a grade for a class as a B instead of an A.
So now you're having to go back in.
So, well, now I can't change it, so I've just been emailing all the schools being like, oh gosh, this
So
was
sorry. That's too bad, but
I think it should be fine, because it's not gonna lower the GPA that I already entered. And they already accepted me for the tag agreement for Davis, so,
then yeah,
I mean, if they see that it's an A instead of a B, it's gonna be technically a higher GPA, and
right,
I mean, there's not really much.
yeah, you should,
I
that should.
think I should be fine with
Yeah.
that, but if it was lower, then that would have been.
You would have to get in touch with the UC application system and actually get them to change it, and it's all too late for that.
And,
Yeah.
Well, that's such a weird one because it was introduced like so early on.
Yeah, that was the first, I mean, it was the first peroxide
Yeah.
mechanism of went over was that.
I remember when I was studying, I was like, "These aren't for this shit."
Of course you did. I didn't even look at it.
The alpine one, of course, same thing.
Yeah.
I thought he was gonna give us. The only one we actually gave that I studied was the oxidation.
Oh, yeah.
That was.
So. Yes.
It stresses me out so much.
I had like a big old stack of my papers just because I hadn't started to fill it up over the phone.
Oh, yeah, you just didn't bring shit out.
Yeah, and on Tuesday he gave me the stack back and like he said he graded it, but there was no feedback on it. It was just all tens throughout, so I feel like I'm just going through and just looking more for completion than any kind of right answers.
My goodness. That's the same thing. So how's it been going with calculus and that?
Bruce hasn't graded, I mean, physics, he hasn't graded anything, but
I mean, I would imagine.
the assessments are okay.
Well, you know, that's actually good for you because you don't actually have to turn in this sort of.
I haven't done any homework. I haven't done any homework. There's no need for it.
There's no need for it, yeah.
So I've just been studying like the UC Davis questions, because those are gonna be the ones that he gives us, it seems like. He gave us a couple of the questions that are on the UC Davis website.
So that's actually what I was studying when I was in my class. No. Because he likes to throw some weird shit in there. Like.
Sort of appreciate it, because it's like, you still have to like think on your feet while you're doing it, so.
Yeah, you have to think about it, it's not just. But, you know, of course, at the time, I wasn't thinking like that, and I was more thinking that I just want the class to be over with.
Yeah, I
I
feel
was
the same.
complaining about it the whole fucking time.
I feel the same, 50% of the class.
Which is probably why I got a C in the class, because I was complaining the whole time instead of actually studying, but.
I just have.
So learn from my mistake, don't complain about it.
I haven't been, everybody's been complaining about how hard it all is, but I was like, oh, it's pretty reasonable and like right on track for what I was expecting.
Yeah, no, like with Atticus, poor guy came back from
The first assessment, he was all mad. Yeah, he was all
and
mad.
I told him, I was like. Don't let your hopes get down for the rest of the class, because then you'll end up like me with a fucking C.
Well, the problem is he didn't attempt like half of it. He only attempted the ones that he thought he knew.
Yeah.
So he only got 2 out of 4 that he
So
tried.
how many did you get the first time?
I got 4 out of 8.
That's fucking great. That's how much I got the first time, 4.
Yeah, and I just didn't study U substitution. I only studied the A1. So U
Well, you
substitution.
get that fucking thing out of the way, boom, you're on the road to a C.
I got A1, I got M7 and M6. No, M6 and M5, which are
M6 and M5 are like the
trading log.
trading the log ones.
U substitution ones, and I didn't get U substitution, which was M4, which is the stupidest thing. 'Cause you
No,
need
you'll
U
do that, but I
substitution.
think you'll get used to, if you just, I mean, just going through the assessments, he'll give you random shit.
Yeah, you'll be cool about it, but he didn't give me U substitution, but he gave me the trade,
Which requires
U substitution and the logarithms. And I didn't do the first one either, fundamental.
We're talking about Bruce's old
Ungrading.
Yeah. He
ungraded.
still hasn't graded anything for physics, though.
Well, so I know you were pretty outspokenly not a fan.
Yeah, it's not-
Are you coming around to it, or are you just resigned and?
I feel like it was just, I don't know, I have to be forced to do something that I'm not the most stoked about. Like with chemistry and with organic chemistry, I love studying it and I spend a lot of time studying it because I like it. With calculus, I have to be forced to study it.
Yeah. Which is hard when there's no
Which is hard.
assignments,
No assignments.
or the
That was
assignments
my
aren't graded,
mistake.
yeah.
Like Like if I can't get like a bunch of feedback on what I'm doing wrong, it's kind of hard for me to succeed.
Right, and so that's why I've toyed with the idea of making. The Gen Chem structure is kind of set up. The way that I left it, but just in general, I've toyed with the idea of making all of the ICAs and all of the quizzes optional. And like you can choose to do them if you want that, if you don't think you're gonna do well on the test, but
But I feel like.
I wouldn't
the
do that.
ICAs really helped me
right,
because. They were mostly harder than the stuff that was on the exam, but
Right.
it actually made you like think about it and go a lot more into depth about the
Right.
topic than if you were. to
It's-
just-
even if the assignment was there, if it was marked optional. I don't know about you, I wouldn't have done it as a student, like, oh, this is optional, I'll look at it, like, I know how to do the first 2/3 of this, I'm like, I'm fine, yeah.
I haven't done anything. Same thing, like.
Yeah.
Yeah.
I mean, by making it mandatory, like it creates a ton more work for me and for you, but it forces you to do the studying.
Right.
And it gives people that don't do well on tests a whole lot of extra points to sort of pad their grade, right?
Yeah, so it's just
Versus
Yeah.
the opposite, that it gives the easy questions as examples and then on the test, he gives. the
oh,
hard
it's
ones.
just- oh, yeah, you get the ones that just have every little thing. Yeah,
All right.
that's cool.
Good to know. And plus, I feel like the Gen Chem tests are already kind of like that, it's like, here's the 10 things you were supposed to learn, right?
Yeah, like the major topics in
And
class.
like, yeah. It's just not doing the retakes part. All right, so is there anything tricky about this top section?
No, just remember
For all of these, regardless of what metal you're using, if it's column 1 metal, it's gonna do the same thing. If you want to get really technical, then you wind up with the lithium salt here, TBOK. No, not TBOK, Li. TBOLI here versus the sodium salt, but the alkoxide ion is the same in every case. You just find the oxygen, pull off the hydrogen, leave it with a negative charge.
those are all created anions now.
Correct. An alkoxide ion is always gonna be an anion. So ranking these based on acidity. Same number of carbons, same number of oxygens. So there's no resonance stabilization. There's no induction. So because this one has less sterics,
Right.
it'll be more acidic.
Thank you.
Yeah. And we would also expect this one to have a higher boiling as well. Solubility gets tricky because the shape of the cavity we make actually affects it, so solubility is tougher. But because this one's long and linear, it can nestle in more closely with the other molecules.
That one's
and have more
sterically, the other one's sterically chunky. You can't
Right.
really-
you can't actually get these ones that close together, so it's not gonna have as strong interactions. So for similar but slightly different reasons.
Right. This one's a little tricky.
So
Because you have the electron drawing groups that are kind of,
So the one on the left is more acidic.
correct,
yeah.
the more you pull electron density away from the oxygen, the more acidic it is. Because there's less of a negative charge to hold that hydrogen on. What's the most important of those 3 variables?
Resonance.
Resonance, one has resonance and one doesn't, right? More acidic.
More resonance, right?
Well,
The
there's
way
more
we get-
resonance on the right, but there's also ketone.
and that's also an electron withdrawing.
which is also like.
The oxygen's So if you're unsure, just see if we put a negative charge here on the oxygen. Could we resonate it out to there? Do we actually gain more resonance? By having, that depends a little bit on the position.
Right. It's a little.
Right, so if
Expensive.
this is what's called the para position, para just means opposite on a benzene ring. Ortho. Is directly adjacent to something else.
And then
Meta
that is on the.
is one swap removed. And para is opposite. So in the para position. We have an oxygen with a negative charge here. So we put a negative charge there, which means we can put a negative charge there. Which means we can put a negative charge there.
Yep.
So putting this group, putting this ketone in the meta position is not gonna have nearly as much effect, if any effect. Because in the meta position, you can't put the negative charge on the meta carbon. If you can't put the negative charge on the meta carbon, it can't resonate out into that other oxygen. So in this case, that actually winds up, this is good review of resonance structures before we get into aromaticity in more detail. Because it turns out ortho and para have a lot of similarities because they can both be resonated to. Versus meta is actually very different, behaves very differently because of the resonance entirely. All right, so here's some other ways, here's just a review of ways we have of making alcohols. So we've seen spent a lot of time with these, right? Hydration reactions are our #1 go-to. Acid catalyzed hydration, if you don't care about rearrangement or if you want rearrangement. Oxymercuration, if you want the Markovnikov. With no rearrangement, and then the hyperboration oxidation. If you want the anti-Markovnikov. Right, so every one of these chapters is. In the Klein textbook especially, are kind of designed to be when you go back. If you went back 5 years from now, you're not gonna remember. All the specifics of all of these, but if you just wanted to look at the chapter on alcohols. To remind yourself, how do I prepare an alcohol, how do I make an alcohol? They're all sort of cross-reference, that's why there's sort of like a lot of back and forth between the different chapters. It's because it's designed to be a textbook you can go back to and review really easily 5 years from now.
You kind of build on certain topics.
Exactly.
This first reaction. is just one.
Yeah, technically it's plus water. And that's it, dilute with the dilute.
Yeah.
Because what are you diluting it in? But it should be more explicitly labeled, I would agree for sure. All right, so let's talk about redox, because reductions and oxidations are gonna start being more and more relevant as we start adding more and more oxygen containing functional groups. And so this is just a review of formal charge. All right, so formal charge works pretty well for the way we think about alchem. Is we basically just look at how many electrons does something have minus how many electrons it has on the periodic table. If you have extra electrons, you've got a negative charge. If you have too few electrons, then you're got a positive charge. And in this case, just like with most of the things in alchem, we're assuming that everything has a full valence. Unless it's explicitly drawn out. to not have a full valence, we can assume that any atoms that are shown have a full valence, with the exception of carbon cations. And the radicals we consider explicitly shown, so you can't have a radical with a full valence, just because that's how even numbers work. Right, and reminder that owned means we're talking about that electrons that are in a bond. The atom only owns half of those.
So like the carbons 4.
Correct, so a carbon with 4 bonds has a formal charge of 0. Right, so this is all similar, this is the way we've been talking about this the whole time, right? When we talk about oxidation state, it's kind of like talking about charge, but it's not formal charge that we're talking about. It's a little bit more abstract. Right, so with oxidation state, we basically just assume whatever is more electronegative owns all the electrons in that bond. Neither of these is the actual truth. It's more complicated than that. These are just two useful ways of thinking about it. And they're useful for different reasons. Formal charge is useful for thinking about what valences are and general stability. Oxidation state specifically is talking more about electron density. So whatever's more electronegative gets to keep all the electrons, and then you still go back and you compare it to the periodic table. I keep pointing over there like there's a periodic table. They don't want us to put up periodic tables because technically all classrooms are supposed to be able to have any class taught in any classroom. But we have all the anyway.
So the oxidation state of that oxygen on the top would be 6.
So you're still going to compare it to the periodic table. So the oxidation state of this oxygen, remember that it's also got a bond between the oxygen and the hydrogen. So the oxygen actually has 8 electrons. So its oxidation state is -2. Because it's got 6 on the periodic table. And oxygen in general is most stable when it's a -2 oxidation state. And since the only thing more electronegative than oxygen is fluorine, unless fluorine is involved, or you have oxygen bonded to another oxygen, oxygen's always going to be a -2. Right, so peroxides, they get that name because if you have 2, so we have water, oxygen's got all 8 electrons, right? Oxidation state of -2. We look at hydrogen peroxide. Well, now what do we do with the oxygen-oxygen bond? Since they're both equally strong, they each get 1. So you treat it like it's a homolytic cleavage. So in this case, this oxygen's got 7 electrons, not 8. So it's a -1 and a -1, as opposed to a -2. And oxygen as a gas is going to have an oxidation state of 0. Right, so oxygen is a gas, and peroxides are when oxygen is most reactive because it's not a -2. Once oxygen's a -2, it's relatively stable. We might see a little bit of substitution reactions or acid-base reactions, but we're not going to see any real redox reactions here because the oxygen's already so stable and so strong. Carbon, on the other hand, because it's in that middle ground between metals and the non-metals, it's not super electronegative, but it's more electronegative than hydrogen in the metals. And so carbon actually winds up having a lot of possible oxidation states. Basically, carbon can have an oxidation state that's literally anything between -4 and +4. Right, that's one of the things that makes it so flexible, so reactive, so it can kind of be anywhere along the spectrum. What could hydrogen have? Hydrogen only has 3 possible oxidation states as well.
-1, so 1.
So here's +1, right? But what if you had, we just did a reaction with sodium hydride.
Right, where it's negative.
When the hydrogen is attached to a metal, it's more electronegative than the metal. So it gets to be a -1. And it'll never be anything beyond -1 or +1. Because it's only got a 1s orbital, right? And so it can only have a total of 2 electrons, period. You can't get a +2 charge on hydrogen, because it's only got 1 proton. And it's only got 1 electron it can give up, right? So hydrogen is always gonna be -1, 0, +1. It's a -1 when it's attached to a metal. Or something that's less electronegative than it is, so like boron, for instance. It's a +1 anytime it's attached to any non-metal,
It's like carbon.
so like carbon. And it's a 0 when it's attached to itself, when you have hydrogen gas. Right, so this, looking at all the different carbons individually, now that we're in OChem, this makes a whole lot more sense for oxidation state than back in Gen Chem where we had to treat, if I gave you ethanol, it would have been C2H6O, and if we're trying to figure out what the oxidation state is on everything, it doesn't make any, we don't get an integer number for the carbons. Because our carbons are not the same oxidation state. So what are the oxidation states for each of the carbons here? How many electrons does this carbon have? It gets none of those. It gets all of those, so there's 4 and it gets 1 of those, so a total of 5, so it's got 1 extra electron. So that's a -1 oxidation state. Compared to here. It's -3 oxidation. Versus here. We get a -2. Right, so when we're talking about oxidation state of carbons in OChem especially. We're gonna be talking about individual carbons, not the molecule as a whole. Right, and anytime we make more carbon oxygen bonds or carbon chlorine bonds. Carbon to anything more electronegative, that's gonna be an oxidation reaction. Because, and from the point of view of the carbon will have lost electrons to do that. And anytime we add a carbon hydrogen bond, that's a reduction. Adding a carbon carbon bond depends on what it's at the expense of, right? Because if we broke a carbon oxygen bond to add a carbon carbon bond, that's a reduction. But if we've lost a carbon hydrogen bond to make a carbon carbon bond, that's an oxidation technically. But in general, the normal rule is if we added carbon oxygen bonds, that's oxidation. If we removed carbon oxygen bonds, that's a reduction. Those are the most common redox reactions we see. Alright, so here's a bunch of carbon oxidation states. Fully oxidized carbon is CO2. You can't get more oxidized than 4 oxygen bonds, right? There is one, is there another one? Hang on. No, there's a hydrogen in there. I was gonna say formic acid. Yeah. So our fully oxidized state is CO2. Our fully reduced state is an alkane. The most reduced it can be is methane. Technically, ethane is going to be a -3, right? On each of the carbons because there's that carbon carbon bond. So basically, this is what the electron transport chain does in eukaryotic cells to produce energy. it basically says, okay, if we expose a fully reduced carbon to oxygen, there's a lot of energy that can be released by going from fully reduced. And it's really that the energy is actually more from the oxygen than it is anything else. Because the oxygen gas is so unstable as it is. Because oxygen's got an oxidation state of 0 there, and it's so electronegative, it really wants to get to the -2. So if you put oxygen in the presence of a reduced carbon, it will spontaneously, in the delta G sense, not just all at once, it will react downhill in energy to make CO2 if you have enough oxygen. What the electron transport chain does is it does it in a series of steps. We don't actually start from alkanes, just because our body's not adapted to digest those. But alcohols, and including sugars are alcohols, right? Like we talked about earlier. You start with a bunch of -2 carbons or -1 carbons, depending. And gradually break them down in a series of steps to get to CO2. And every time you do that, you generate a pair of high energy electrons. And those high energy electrons are what generate the ATP. But it's this stepwise process. Every time you make a pair of high energy electrons, it can be used to send it through the electron transport chain. And that all that really does is it creates an energy gradient in the mitochondria, where we basically have a high energy state where you have a whole the concentration of H plus or hydronium inside the mitochondria is really high. And when they go downhill in energy to cross the mitochondria, they wind up producing ATP. In the process of them going from a high concentration to the low concentration, this process is that it's one of the coolest things. It blew my mind when I first wrapped my head around this, and when I was in college. It's literally like physically turning a windmill.
Yeah, it's like the ATP synthase is literally like a rotor.
It physically moves like a rotor, and it's these protons moving across that gradient that cause it to rotate and turn. And it basically just grabs an ADP and a phosphate, and it shoves them together and holds them there until they turn into ATP. And once they turn into ATP, it lets go, and the windmill rotates 1 more notch. So it's weird that you can have a physical change causing a chemical bond to form at that scale. That was something that was totally foreign to me when I first took cell bio. But it literally is grab these things, force them together, because we've got a concentration gradient instead of like water flowing downhill, but it works the same way. You've got a force pushing these things through this windmill, this water wheel. And in doing so, you cause a physical change to happen. Right, and we wouldn't be able to do that nearly as effectively if our body just straight up burned methanol or sugar. You can burn sugar, you can release all the same energy, but you release it all at once. And if you do it all at once, you don't get all of these different pairs of high energy electrons that can feed into making that proton gradient. Right, so you do it one step, you go from an alcohol to a ketone or an aldehyde, depending on the specifics of the Krebs cycle and where you are. And those pair of electrons make an NADH or an FADH2. Doesn't matter the specifics of the molecule. You make another pair of high energy electrons that are going to go and make a lot of protons inside the mitochondria at the expense of protons outside the mitochondria. So all we're doing every time we make an oxidation step here, that's just going to create more protons, more H3O plus inside the mitochondria and build up that pressure, like adding 1 more bucket of water to the top of the water wheel or to the top of the stream that's then going to flow through the water. We did it all at once. It might be really easy to take your 4 buckets of water and put them in a catapult and launch them to the top. That's not going to be as effective at getting as much water into the top of the stream, right? you're gonna have a lot of water splashed all over the place. You'll get some of it there, the same total amount of water made it there, but it's not all useful. And so doing it in specific steps is how that works. It's, again, tying together OChem and bio and cell bio was really cool. That's one of my favorite parts about upper division biochem. Was that we actually looked at the chemical structure instead of just, here's an NADH, this is what it does. We actually looked at, this is the bond that's reacting with this bond in the protein in the electron transport chain. And looked at the chemical reactions of every step instead of just memorizing, this is the electron transport chain, here's what it does.
Memorizing it's kind of boring, but you actually look into.
When you're actually looking at the mechanisms, the actual electrons changing hands, so to speak, I really enjoyed that, obviously. All right. Last thing I want to go over today is just practice. Each of these, a redox from the point of view of the carbon. Is it a reduction, oxidation, or neither? Neither. The same number of carbon-carbon bonds. And we switched out the oxygen for 2 chlorines, but chlorine is still more electronegative than carbon. So whether or not this is downhill in energy is beside the point. The carbon has the same oxidation state in both cases. You could probably split hairs a little bit. Because the oxygen is more electronegative, but one of those bonds is a pi bond, that you could really get into the weeds as to the actual electron density around the carbon. But for the point of view of most chemists, you're just looking at oxidation state and it's the same.
Does resonance play into oxidation state in any way?
That's a good question.
If we resonate this one,
It wouldn't be because you'd be putting a positive charge on the carbon.
Right.
So you'd be taking the pi electrons that between the oxygen and carbon, giving them entirely to the oxygen, but for oxidation state purposes, we already did that. So I'm sure that there are some cases where different resonance structures have different oxidations on individual carbons. But in general, that doesn't come up as much. I'll be paying more attention to that now.
We were talking about the first rule of the last thing's resonance, so.
No, that's a good question, and I'm just trying to think. As usual, I'm not gonna answer with an absolute. How about here, aldehyde to a carboxylic acid? We took away a carbon hydrogen bond. And we turned it to a carbon oxygen bond. You might be, there's a reason that oxidized is called oxidized, because usually it just means you added more oxygen into the system, it's also going to be oxidized. Because the oxygen is going to be -2 in both cases. So from the point of view of everything else, our carbon here has an oxidation state of. I don't think it's 4, so, oh, sorry, it's got 3 electrons, because that's a carbon. So it's got an oxidation state of +1. And here, it's got an oxidation state of +3. Because it lost the 2 electrons, the carbon owned the 2 electrons here. And it doesn't here, because we added the big volume to the system. Right, so. +3 to or +1 to +3, the carbon lost electrons, it was oxidized. Carboxylic acid to an alcohol. Yeah. So we still had a +3 here. So this carbon doesn't change in any of these, right? This carbon's oxidation state stays the same. Here we go from a +3 to now this carbon has 1 2, 3, 4, 5. So it's a -1 here. Right, and so this is what plants do. Is they take CO2. Well, the reason we think of them as breathing CO2 is they take in CO2 when they're photosynthesizing. And it's called carbon fixing. Is when you take CO2, carbon's the most oxidized state, and you reduce it. And you turn it into something that the plant can then store energy. And it takes energy to do that. You're going uphill in energy, you're fighting against the energy gradient. But it's basically like using solar power to pump water uphill. And then when you need electricity later, you use it to spin a turbine. You're pumping the water uphill so that then it can turn the turbine later when it's dark outside. That's what plants are doing, because plants actually burn sugar at night, right? When the light's not shining on plants, they're actually breaking down sugar the same way that we do. They're eukaryotes and have mitochondria the same way we do. They just also have chloroplasts. And those chloroplasts are basically the solar cells that allow them to stash energy for the time when there is no sunlight. Right, so carbon fixing is a huge research area right now, because what is one of the biggest problems with scaling up solar energy is what do you do when the sun's not shining, right? Batteries are a partial solution to that, but yeah, that's using battery power, right? You're using
Tesla that has like the gas motor strapped on the back.
Exactly. So one of the ways that you can use batteries, but batteries aren't very mobile because they're very heavy, right? That's one of the problems with electric cars. They've gotten better and they'll continue to get better in all likelihood. But one of the other really big research areas is, well, what if we could just create an artificial photosynthesis to take us all the way from CO2 to ethanol? Ethanol we can burn. We can actually just use an internal combustion engine. We tweak the metal and we tweak the production. We can actually just throw ethanol or something similar into a gas tank.
It's just fuel injectors, right?
Right. Pretty much. And so with that in mind, that's a carbon neutral process then.
Yeah.
If you're starting from pulling CO2, the problem with internal combustion engines is not that they're internal combustion engines, it's that we're taking all the CO2 or all this carbon that was sequestered under the surface of the earth for millions of years and putting it back into the atmosphere. If we started by pulling it out of the atmosphere, made a liquid fuel with it, burned the liquid fuel, there's a lot of inefficiency there, but we're really well set up to be a liquid economy when it comes to delivering things. Everybody knows how to work a gas pump. You don't need to teach people new things. We already have all of the laws in place for transporting ethanol for that matter. One of the problems with electric vehicles is that fire departments can't handle burning batteries, right? It's a huge issue.
On fire is
If you
not really
yeah,
the best thing to
exactly.
deal with.
If you spray water on an EV fire, it just explodes, and then you have toxic waste everywhere, literally.
Isn't that like a flashbang too?
I'd have to look at the specifics, but it's not gonna be good.
Yeah. I'm pretty sure it's the same thing as a flashbang, it's lithium metal, water.
That's, so flashbang, what actually makes the flash part of it is magnesium.
Oh, it's magnesium? Okay.
Yeah, because magnesium burning is that super bright white light.
Gotcha.
But so anyway, this is an ongoing, and they don't call it artificial photosynthesis for whatever reason, they call it carbon fixing. Or nitrogen fixing if you're starting from N2, that's a big deal in agriculture.
So that's like with bacteria will do that.
Right, bacteria, and that's why legumes are so important, beans are so important for crop rotation cycles. Is because beans actually have evolved to have these little, I think they call them nodules on their roots that harbor these bacteria that take atmospheric nitrogen and turn it into nitrates and ammonia. Which is, so if you're depleting your soil by farming corn year after year after year, if you put farming beans in there, you can replenish some of that nitrogen into the soil without using artificial fertilizers. But and the engineering and agricultural term for taking carbon and turning it back, CO2 and turning it into a fuel source, or taking nitrogen and turning it into a nutrient for plants is fixing, nitrogen fixing or carbon fixing.
Fixation, carbon fixation,
Same term.
same thing.
Yeah. As far, maybe I'm saying it wrong. It's been a while since I've been in.
It's been a while since I've heard of it, so exactly what it means.
Yeah, I'll have to double check that. I think it's carbon fixing, not, the carbon fixation would be talking about the same thing.
I think it's carbon.
Either way, what you're really doing is you're reducing carbon, and that's the
Right.
point of today's lecture. And we'll end there for today. All right, so for this weekend too, we'll just do the quiz this weekend will probably just be some more, is it an oxidation reduction or neither questions? So, and maybe a little bit of alcohol nomenclature.
Probably acidity questions too for alcohols.
It's a possibility.